All right, should we get started? So obviously, Professor Mutlu is not here this week because he's traveling to a conference. So it'll be me this week. So you guys should have some fun. All right, so how was your spring break? You guys spent a lot of time studying 447? Yes, I see a lot of nods. OK, so I guess maybe some of you did enjoy spring break. All right, so today will just be a short recitation on what we have done in the last lecture. And we'll also be answering some questions regarding labs and homework. So first of all, just some reminders. Lab 5 is going to be due this Sunday, or next Sunday, March 22nd. And it's going to be on the data cache. And homework 4 is due this Wednesday, March 18th. Most importantly, you're going to have your first midterm on Friday during the lecture time, 12:30 to 2:20 sharp. And so please try to arrive early and make sure you sit with one seat in between you and your neighbor. It's going to be closed booked, closed notes, but you are allowed to bring one cheat sheet, double-sided. So you can do any tricks you want on that one single page. And so all the past midterms have already been posted on the website. I strongly recommend you guys going through all the past midterms. And that will help you a lot on preparing for this midterm. So mid-semester grade. So here, what I'm showing you is the distribution of your grades. So the bins here are based on the grade percentage you have earned so far. It will become 100% once you reach the end of semester. But so far, the maximum is 21% out of all your homework and labs. So the maximum is 21, but obviously you can see some people earned well beyond 21s because from the extra credits. So that's why we encourage you all to try to work on extra credits. It gives you lots of boosts on your percentages. And the letter grade assignments based on this percentage is posted on AutoLab, so you get to see it. And if you want, you can calculate these percentages by yourself as well. So if you don't have any questions on this mid-semester grade, I'll just move on. Yes, Ashish. Huh?
Are our mid-semester grades up on
AutoLab.
AutoLab?
Yeah, so you can check it out. Yeah. Anything else regarding mid-semester grade? OK, so we'll just do a quick review on the last lecture. So what we have done is we went through virtual memory. So what is virtual memory exactly? It's essentially a level of indirection that provides you an illusion of extremely large address space while you only have a small physical memory. So in today's system, we have 64-bit address space. So what does that give you? So 64 bits gives you 16 quintillion bytes. And obviously, that'll be way too expensive to implement in today's system, having 16 quintillion bytes of DRAM for your main memory. And so that's why we have virtual memory to provide you this illusion of having this large space while we only have a couple gigabytes of physical memory. And the second point here is so this illusion is provided separately for each program. So what are some of the benefits of virtual memory? The first one is virtual memory uses the physical memory very efficiently. So if you think about physical memory or DRAM, it essentially is a cache for your disk. So with virtual memory, you only cache those pages or data you need to access inside the memory. So you don't have to basically cache in or bring in every single pages that your program is going to access. You only need those that have high locality or those that you are going to access in the recent future. The second benefit here is simplicity. So with this automatic management by both software and hardware, the programmer is relieved from the burden of figuring out how much memory your program is going to use and how much memory is available in your systems. So you also don't have to worry about which are other programs in the system and how much memory they're actually using. So you just have this illusion of huge 64-bit address space you have. And you don't have to worry about the rest. So it makes your life, or the programmer's life, much simpler. And the last point here is safety. So with this separation of address space, it can prevent other programs from accessing your data. And so it also prevents certain programs from accessing every single page in physical memory. And this gives you an extra level of protection. Any questions on virtual memory so far? OK. So what are some of the basic mechanisms of virtual memory? First and most obviously is you have a virtual address space provided to your programs through your system software, the kernel. And the second point here is you will need to perform address translation somehow to translate your virtual addresses to physical addresses. And we talk about a data structure called a page table that stores mappings between virtual addresses to physical addresses inside memory. And I think we've gone over two major problems with page tables. The first problem is that it can become too large, consuming too much memory, because there could be too many pairs of mappings between virtual addresses and physical addresses. So you don't want to store all that. You don't want to unnecessarily store that information in your memory. So what we have done is, or what we've discussed is that current systems, what they do, they add another level of indirections by building hierarchical page tables. So I think Professor Mutlu have gone through this. He went through the examples of having page directories and page tables, multi-level page tables, essentially in x86, and you can review that in the last lecture if you want. And the second problem is that using page tables can become too slow, because whenever you want to translate a virtual address to physical address, you will first need to go into the memory to look at your page table to figure out the mappings. So that's going to increase your access latency of your memory instructions. So the solution we examine is that system today has employed a small cache structure called the TLB, the translation look-aside buffer, to cache those recently translated pairs from virtual addresses to physical addresses. So this helps mitigate the long access time of page tables by using a small cache called TLB. So one important issue we talk about is when do we want to perform translation? Do we want to do it before or after accessing your L1 cache? So there are essentially two addressing modes that we talked about. The first one is we use virtual address to access the cache, or we use a physical address to access the cache. So they're also called virtual or physical caches, respectively. And there are two major problems that comes with these caches, these different addressing caches. So the first problem is the homonym problem, where you have the same virtual address mapping to different physical address. So the problem here is that you can, with the homonym problem, you can access incorrect data. So with the same virtual address, you don't want to access a completely different physical address, given that it can map to multiple physical addresses. So the reason why you can have different physical addresses being mapped to the same virtual address is that the virtual addresses can be in different processes. So you can have two processes having the same virtual address, but being mapped to completely different physical addresses. So the second problem here is a synonym problem. This is a problem where you have different virtual addresses mapping to the same physical address. So this will introduce a coherency problem, where imagining having one process writing to a physical address. On the other hand, you have a completely different process with a completely different virtual address that is mapped to the same physical address. So in that case, if you have a cache that stores multiple copies of the same physical address, they're going to be out of date if one process is going to perform a write. And the reason why this can exist is because different virtual pages can share the same physical frame due to shared libraries or copy on write. And there are also multiple other reasons why synonym problem can exist in your cache. OK, so here are three options on how you can access the cache with virtual addresses or physical addresses. So the first option is you perform the translation first, then you only use physical addresses to index your cache. So here, when we talk about cache, we're really talking about your L1 private cache. And the second option here is you will only use virtual addresses to index your cache, then you perform a translation afterward. The third option here is you try to use try to use both virtual addresses and physical addresses somehow. So you will simultaneously access your TLB and cache at the same time. You will only use virtual address to index the cache, but you will use the physical address to check if it's a valid cache hit or miss in your L1 cache. And what are some of the trade-offs with these different options? So with the physical cache, you wouldn't have any homonym synonym issue because you're only using physical addresses. And the problem here is you may have high latency, high access latency to your fast L1 cache because you're increasing your critical path by putting the TLB before your cache. The second design here is a virtual cache where you only use virtual addresses. In this case, you have both homonym and synonym problems because you're only using your virtual addresses or virtual bits. So this can cause conflicts in your cache. But the upside here is you will have very fast latency, very low latency to your fast L1 cache because you only perform the translation after you access the cache. So how do we get the best of both worlds? And this is where the third design comes up, where you try to use both virtual address and physical addresses to access your cache. So in this case, it doesn't have the homonym problem, and it potentially might not have the synonym problem. We'll look at these two problems in detail in the next couple slides. And it will also have very low latency to your L1 cache because you're doing simultaneous accesses to both TLB and your L1 cache. So let's take a look at this virtually indexed and physically tagged cache. So here's a high-level block diagram and on how to access your TLB and physical cache. So let's focus a little bit more on your virtual address. So here, the virtual address is broken up into two parts. The first part is the virtual page numbers locating at your MSBs. And the second part is your physical page offset, which you use to access bytes in the physical page. And so how do we decide which bits to use as index bits to access your cache? So when your cache, in this scenario, we're assuming your cache capacity is going less than your page size times the associativity of your cache. So in this case, it will guarantee that you will be always using the page offset bits to index the cache. So one thing to note here is the page offset is the same between your virtual address and translated physical address. So this is a key here for the virtually indexed and physically tagged cache. So next, we'll assume both TLB and physical L1 cache locate on chip. And we index both structures concurrently using virtual address bits. And we check. So after you index your physical L1 cache, you will use your physical address, the physical page number, to check if it's a valid cache hit or miss. So your tag essentially is your physical page number from your physical addresses. Okay? So with the addition of physical tag, this eliminates the homonym problem. Does that make sense? Or do you guys have some questions on why it eliminates the physical tag problem? Yes? No? I guess yes? OK. So basically, so homonym problem is where you have same virtual address mapping to complete different physical addresses, right? But if you even if you have the same virtual address going to the same set of physical cache, as long as you have the physical tag, you can distinguish different different physical addresses. So that's why you eliminate the homonym problem. So you'll ensure that you're always accessing the correct physical addresses with your physical tag. OK. So next problem is the synonym problem. So this problem occurs in this design. So no. So in this particular setup, the synonym problem is not going to occur because you're always using the index bits from your physical page offset. So the synonym problem, again, is where you have different virtual addresses mapping to the same physical address. And remember the key observation here about page offset? They're always the same between your virtual address and physical address. So even though you have complete different virtual addresses, you're guaranteed that the page offset are the same as long if they map to the same physical address. So therefore, in these scenarios, they will always go into the same cache line where you only have the same copy. You only have one copy of physical address in your cache. So when does synonym become a problem? So this is a scenario when when the synonym is going to occur, where your cache size is greater than your page size times associativity. So this means your cache index bits are going to include some part of your virtual page number. So if we zoom in a little bit on the virtual address again, you can see that if we increase the cache size, the index bits, you start using the virtual page numbers for index bits. So this will reintroduce the synonym problem because with different virtual page numbers, they can go into complete different cache sets. That means you may have multiple copies of the same physical address. And that's going to create the coherence problems. Then what are some of the solutions we talked about last time to address the synonym problem? The first option is the simplest, is to simply limit your cache size. And basically, it's this formula right here to ensure that we're always using the index bits from the PPO. And the second option here is whenever we perform a write to a block in the cache, we basically find out all the possible indices that can contain the same physical address. And we update and we update and invalidate based on that. So the third option here is we can try to restrict the page placement in the operating systems. So what we're going to ensure is we're making sure some of the bits from virtual address, this is completely same as physical address. What this means is that blue box there, we're going to ensure those bits in the blue blocks are going to be the same between your virtual address and physical addresses. So that's going to ensure the index using virtual address is the same as index of using physical address. So this technique is also called the page coloring. And I don't think we require you to know too much detail about page coloring. But I think there are some papers or readings we're posting online regarding page coloring. So if you're interested, you can read into it. So does anyone have any questions regarding the synonym versus the homonym homonym problem in the virtually indexed and physically tagged cache? Yes, Raga.
Can you go over the homonym problem again? Because synonym, you're just taking the bits from the thing.
Yes, so you're talking about virtually indexed physically tagged cache?
Yeah.
Yes. So you're asking why isn't there a homonym problem?
Yeah.
Okay, so the homonym problem again is where you have the same virtual address mapped to different physical addresses, right? And in this case, what we need to know is that page offset is essentially a physical address, right? So even though you have the same virtual address from complete different processes, the bottom some number of bits, or PPO, are going to be the same because they're mapping to the same physical page. Correct? Okay, so now we're only going to use the index bits from the page offset to access the cache. So even though I have complete different virtual addresses mapping to the same physical address, I will always be going to the same cache set. So that means I only have one copy of data inside my cache. Because if you have this, let's say I'm sharing two processes sharing the same library, I want to make sure we read the same piece of code. We don't want to read complete different data or code. Does that make sense? Okay. Yes.
The tag bits will be different in both the cases, right? If it's two virtual addresses.
the tag will be the same. Remember, we're using the physical page number for the tag.
Okay,
We're not using the virtual address for the tag.
okay.
Yeah. So this is the key here. So the tag here is basically your physical page number.
Okay.
Yeah. So you do the translation first, and you use the physical page number as your tag.
Okay.
Yeah. So that part is completely physical. Yeah. Any other questions? Okay. So I think we've gone through the reviews of last lecture, and we're going to do a quick exercise on virtually indexed and physically tagged cache. Do you guys want to try to work on it your own, or you want me to walk over it? Any preference?
We first try it. And then
Okay.
go over it.
Okay. Yeah. So why don't I give you some time to try it out, and we'll walk through the questions together. Okay. So let's go through the first part. So it's asking how many bits of each virtual address is the virtual page number. So what I tend to like to do is I like to draw the address first. Well, that's very ugly, but yeah, and break it into two parts, right? So this is your virtual address. And in the handout, we specify your virtual address space, which is 2 kilobytes. So that's essentially 2 to the 11, right? So in total, you will have 11 bits being used to access your virtual address space. The next piece of information, what we need is the page size. In this case, is specified as 8 bytes. So this is 2 to the 3. So we know that the bottom 3 bits are used as the PPO, and the top, I guess in this case, the top 8 bits are used as a virtual page number, right? So answer to the first part is 8. Does that make sense? Okay. So the next part, it says how many bits of each physical address is the physical frame number. So what we need to figure out here is the physical address space size. So in this case is, what's the physical address? Okay, so the physical address space is 2 to the 9, right? It has 512 bytes. And again, we know the page size, or the PPO here is 8 bytes, 2 to the 3. So we know that we only need 6 bits for this questions. It's asking the PPN number. How many bits are used for PPN? So this is your PPO, physical address, PPN. Okay. So in total, your physical address space has 9 bits, and you use 3 bits for the PPO. So the answer to this question is 6. Does that make sense? Okay. All right, so here's the next part of the question. You guys want to go over it together? Okay. So the third question here is, how many bits of a virtual address are used to determine which byte in the block is accessed? So here essentially is asking about the block offset of your cache. So in this case, I think the block size is 2 bytes. So essentially, you take log of 2, which is 1. So for this question, you only use 1 bit of your virtual address to access the cache. So the fourth part is how many bits of virtual address are used to index the cache. So the first piece of information we need is the cache size. In this case, 128 byte. So 2 to the 7. And since we need to figure out is it index? Yes, index. So basically, we take the log of cache size over the block offset, which is 6. Oh, and also ask which bits exactly. So here, in this case, if you draw the address range again, the 1 bit will be your block offset, and here will be your index. Right? OK. So this question is 6. For this part is 1. And for 5, it asks how many bits of the virtual page number are used to index into the cache. So again, I guess we will redraw the virtual address space and draw the PPO and the virtual page number here. So we know that the bottom 3 bits are used for PPO. Then so we can figure out how many bits here are used for the virtual page number. So I think here it will be 4, right? In total, we use 7 bits for the cache and the 1 bit for the block offset. So here we'll have 4 bits of the virtual page number to access the cache, part of 4 bits to access the cache. So in this question, yes, it's 4 bits. So for the next part, has anyone finished the next part? Part 6? Do you want to come up?
I don't think I did it right, but
Can give it a try. Extra credit for you.
okay.
Here.
I don't know if this is right. The way I thought about it was because you're tagging using the physical address is 9 bits, and since you're already using,
Can you move the paper down a little bit?
is that good?
Yeah.
How do I make it it's diagonal? I don't know.
Yeah.
Okay. And we concluded that we're already using 7 bits for the block offset and the index. So I just did 9 minus 7, so I got 2 bits.
2 bits for
For the tag.
tag.
Yeah. I'm not sure if that makes any sense.
So actually, remember, when we go back to the slides, we mentioned that we actually use a physical page number for your tag.
Oh, so it's 6 bits.
Exactly. So if you
Okay.
go back to part 2. Yes. So this question here, this part, we ask how many bits of each physical address is the physical frame number or physical page number. So this is the number of bits we use for our tag. So in this question, this part 6, what we're asking is, what's the size of a tag store? So there are 2 major pieces of information we need. The first one is, how large is my tag, and how many sets do I have, right? So now, I guess we know sort of
So I
tag size.
calculated earlier that there were 64 correctly?
Yes.
Okay. So do you just multiply those two?
So there's actually one more piece of information that we need for our cache. Does anyone know what else we need to calculate the tag store size? So besides these two information, we need something else. Yes.
Right.
Huh?
I don't know.
Oh, okay.
I was going to say valid bit, but
Correct. Yes, valid bit. So we need one extra valid bit here. And you were gonna say right, but remember this is right through cache, so there's no dirty bit. Yeah. So yeah. So this is important because in the future we might go over this sort of questions in your homework again. So just make sure you understand what are some of the bits you need in your tag. For example, basically when you start with, you have the valid bit, you have the dirty bit, then you have your tag. So these are three pieces of information you need to calculate your tag store. Yeah. Well, thank you.
All right.
So I guess Amanda and
Wait, so you add it and then multiply? You do 6 plus 1, 7 times 64?
correct. So basically, your final size is 6 plus 1 times 64.
I have a question about the importance of the italicized word right through. Like, since it says 128 byte right through cache.
Yes.
So, like, would a variation of this question be like 128 byte right back cache or something?
Correct. Then you have an extra bit for 30 bit, right?
Okay.
Yeah. Okay. So here comes the next parts. So go for it.
Is the specification the same as the previous question?
Yes, yes. Does anyone have the answer already? Extra credits.
I have the first one.
Okay, you want to? Oh, sure. You want to come up and write down?
I'm not
your-
sure if it's right.
It's okay. It doesn't have to be completely right. Point is, we'll work through it together.
was that? So page 15 virtually and page 7 have the same frame, which is frame 3. So page 15 and page 7 have the same frame, which is frame 3. So you just write a physical address that corresponds to frame 3. So in the physical addresses, there are 6 bits for frame number and 3 for block or like offset bits.
Yes.
So you can make these 3 0 and you put 3 in this, and then so that's like 1 8.
Correct. Yeah. So, did anyone get this answer? Yes. Go. So, it's just a question or?
I was just saying yes.
Okay.
If you like change the page offset, like the last 3 bits, does it matter what those are?
So in this case, we didn't really specify the page offset.
So it could be 24 to 32, like
Yeah.
Yeah.
Because like I made it like 001 instead of 000. Does that matter?
I think I think it's okay, but yeah. So we're not being very complete clear here,
Okay.
but we encourage you to write down the actual alignment of a page.
Okay.
Yeah. Okay. So how about the next part? Do you want to try the next part too? Part 8. Here.
Give the indexes of those
Two
two
locations
locations in the cache.
Have you done it?
No, I'm like I can do it right now.
Oh, how about we let someone else
Yeah.
try? Chris, you want to give it a try? Here you go. Sorry. Wrong.
Okay, so this is a virtually indexed cache. So we want to find the virtual addresses. So we have this same offset of 000, and then the virtual page number is 8 bits. And so for the process 0, it's 15. So that's 0, 0, 0, 1, 1, 1, 1. And for the second process, it's page 7. So that's 0, 0, 0, 0, 0, 1, 1, 1. And then the first bit is the byte and block, and then the next 6 bits are the index. So the index for process 0 is whatever this number is.
Yeah, it's okay.
28,
Yeah.
And then, yeah.
Yeah, essentially that's the answer we're looking for.
It's not like that. There we go.
Yeah. Thank you. Did everyone get this answer?
The first part again. Like 6.
It's part 6.
One where you
Part 6 is okay. This part 6.
No, sorry, part 7.
Oh, part 7. Okay. Yeah. So you want me to go over it? Okay. Sure. So just different page. Okay. So here, what's asking is give a complete physical address whose data can exist in 2 different locations in the cache. So as we can see from the problem, we give you sort of 2 translations tables, one for process 0, one for process 1. First thing is we need to find one physical frame that is shared across 2 different virtual addresses, right? Does the part make sense? Yeah. So basically, this is frame 3, physical frame 3, and we'll have 2 virtual pages. Virtual page number 15 and 7 assigned to the same physical page number 3. So here, physical page numbers is analogous to the frame number. Yeah? Okay. So now basically we need, remember we went through how many bits we need for the physical page numbers, and I guess part 2. So we go back to part 2 here. we already figured out how many bits are used to physical frame number. So the physical frame number is right here. Correct? So here, we're using 6 bits for my PPN. And we're using 3 bits for my PPO. So basically, we're mapping this to this. So we just write out a number of bits, I guess. 1, 1, 0, 0, 0, and 0, 0, 0, 0. Does that make sense now?
Yeah.
OK, cool. All right. So this is the last part. Does anyone want to try out part 9?
Try.
Yeah, come.
Excellent.
Yeah.
That's worse. See that? Right, there you go. So, and this says you have to use the let's see is less than page size times associativity. Page size, right. And I think that your cache is 128 here bytes. And your page size is, I believe, 8
Yes.
times associativity. So this is 2 to the 7th, less than 2 to the 3rd, associativity. And then so you have 2 to the 4th, is less than associativity. So your associativity is at a minimum 16.
Correct. Did anyone want to see that? We can also do it pictorially. So if we just want to... Thank you, guys. Yeah. So remember this part where we try to figure out how many bits are used from the virtual page numbers. So basically, these are the extra bits that we need to eliminate by increasing the associativity. Can everyone see? Yeah, so in this case, as we calculated before, I don't remember the part. I think, yeah, we calculated in part 5. We're using 4 bits from the virtual page numbers. So basically, this is the number of bits we need to eliminate. And this essentially, we can derive it into 16 ways of associativity. OK? And I think the last part is pretty straightforward. We have gone through 3 different solutions, right? And we already mentioned one solution in the problem set, which is increasing the associativity. So if you write down any of these two solutions, then we'll accept the answer. So one solution is whenever you perform a write, you check all the possible indices, and you either update them or invalidate them. The third one is use page coloring to make sure the bits you're using from the virtual page numbers are going to remain the same as your physical page numbers. Okay? So if you want to go over this exercise again, you can look at the solutions here at this link. And there are many more exercises on similar problems in the past exams, and it's going to be in your homework as well. OK, so we're done with the review of virtual memory. So now we'll take some questions on Lab 5. Does anyone have questions? Yes, Amanda.
Just a really quick one. There's one place in the handout where it says you want the default capacity to be 8
Yes.
and another place
Yes, sorry, there's a typo where we specify 2 default cache size. So please default it to 8 kilobytes. Is there anything else? Someone asked a very good questions on handling writes for Lab 5. So there's a post on Piazza on that. I would encourage you to read over it. OK, so I think we still have some time, and we'll plan on just walking you through one last question that you have done already in your previous homework. So it's on branch prediction. So Rachada will actually walk you guys through the solution to that question. Yeah.
All right. Okay. Do you have a spare piece of paper?
Yes, yes. Oh no. Okay, let's do this one.
Yeah.
That's okay. Okay.
Can barely see it.
You can zoom in.
Yeah. Okay. So, are you guys clear on how to solve part A and part B? Because that's kind of needed for part C. About local correlation and also the global correlation.
Can you just walk through it?
Okay, sure. All right. So, for part A, to figure out if any of them exhibit the local correlation, you have to first realize when you check for modulo, the outcome doesn't, for each time you test it, the outcome doesn't matter. So locally, branch B2, B3, and B4 have no local correlation. So that's the answer for part A. The only branch that has a local correlation is B1. For part B, if you look at the value within each branch, B2, B3, and B4, you realize that 10 is divisible by 2 and 5, right? So that means that there's a global correlation between branch B4 to B3 and B2. Because if I is divisible by 2, it means it's also might be divisible. If it's divisible by 10, then it means it's divisible by 2 as well. And also the same goes for 5. Yeah?
Why does B1 exhibit local correlation?
For that, for B1, because so it's within B1 itself, right? When you loop around, there's a correlation is going to be taken if the previous branch outcome is taken. But unlike that, so for modulo, if you don't know how B1 is being iterated, right? So if you don't know how the progression value of I, then there's no way you can tell whether it's modulo by 2 or not.
Yeah. I'm just wondering, like, isn't B1 like just almost always taken, regardless of the previous iterations of B1? Or
And isn't that local
I
correlation?
get it.
Within itself, right? Because within the branch itself, within B1, you know from history you can tell what my prediction is. But if you don't know anything of B1, in this case, you cannot tell anything of B2, right? If you just look at B2 alone and look at, say, the value modulo 2, which is some random value in the array I, right? It's not the index. So what are you testing here is the value from the array
Yeah.
of some random value. So the previous value in the array has nothing to do with the next value.
Just one more.
Yeah.
So if it's not the random value with the index, then what you're testing
Then you have the correlation.
all
Yes.
If you say that B1 has local correlation, just because it's almost always taken, doesn't it?
No,
also-
because it follows from I, right? If you look at that, he says it's almost always taken because it follows from an index which has been counting up, and you test whether it's less than n or not. So within B1, you can use the history to predict the next taken or not taken outcome. But for B2, B3, and B4, there's no way you can tell because it's just a random value from that array.
Right.
Yeah.
Okay. But like you don't see the index, right? In your local history table.
You don't see the index, but there's a correlation between the history and what will happen in the next, I guess, in the next iteration.
I mean, it just sounds like n is, like, compared to all the other ones, n is your random number this time, and it's just like, oh, hey, what is n? And doesn't that seem to make sense?
But it is dependent on the previous history. But if you look at this random value in the arrays, each value is independent, right? So each test are independent of each other.
I think you would only be able to exploit the local correlation of B1 if your like local history buffer was like at least n bits, right?
Local history buffer?
Like,
You mean you have a 2-level prediction, or it's just like one saturating counter?
so I mean, to
I see what you mean, like log n bits, right? Then,
oh yeah, sorry, log n.
yeah.
No, and like because you would only be able
Oh,
to
yeah,
predict
yeah.
that n is that B1 is not taken if you can see that like it wasn't taken like n iterations ago.
Yes. Oh yeah, if you look at the definition of the table, the prediction over here, then yes. Yeah. Right. So any other questions on part A and B? All right. How about part D? You guys want to give some more time? I mean, you did this in homework already, I assume. Do you understand how to work through this? Okay. So I guess the key here first is for each iteration, what's the expected value of the PHTE? And when you get the expected value for each iteration, you just multiply that number by 120 because you run it for 120 iterations. So the way you do this, anyone want to like come here and solve it? Come on, you did this already. I almost all you get it right. unless you copy it from previous homework.
By first PXT entry, it means the entry corresponding to GHR00, right?
For entries, yes, because GHR, well, the first entry will be the 001. Yeah.
Why is the first entry 0, 0? The way you guys did it, you guys use 1, 1, 1.
Yeah.
Exactly, that's my question. In the solution also they use 1, 1. I'm not
Well,
sure why.
they assumed it was taken. It just depends on your encoding. But 0 could be taken.
Oh.
This question, the first entry is 1, 1. So
Okay.
we didn't specify it.
Exactly.
So
Wait,
that's why.
that's no.
It's supposed to be 1, 1.
Okay,
but
okay.
we
My
just
bad then.
assume you guys know it's 1, 1 based on the lecture examples. Yeah. So it was our fault being ambiguous, but this won't happen on the exam. We
Alright,
won't have
cool.
to guess what the first entry is. We'll specify saying if it's 1, 1, 0, 0 or 0, 1, 1, 0. So we're going to tell that to you.
Okay, cool.
Yeah.
All right, I hope that clarified the thing. All right. Anyone want to take a shot? Really? You actually did the homework? I mean, you guys did the homework. So for what's the I guess contribution of each branch to the expected value? Like let's take, say, let me go back to the actual branch. Let's take B4 first. Any takers? Yeah.
Because the idea is that since you want like taken to be in the global
Mhm.
history
Yes.
register, then both the B2 and B3 should have been taken,
Yes.
right?
Yes.
So you have to, so the probability that those are taken are like 1/2.
Yes, what happened? So, and then yeah.
I found it easier just to draw a tree out, and then with the tree, you can just kind of look at the expected value of going down the taken side. So, it's just what I did. So which side do I have to stand on terms?
I think here.
Okay. So you have branch 1, and then branch 2, and then branch 3, and then branch 4. And then if right side represents taken, then you know that we can assume that branch 1 is, so we have 120 iterations, and then we can assume that branch 1 is always taken because, yeah. And in branch 2 was the mod, right? So only 60 of these will be taken, and 60 of these will be not taken, so we'll just taken. And then in branch 3, of these 60, 48 will be not taken, I'm sorry. And then 12 will be taken. And then you have to consider from B4 to B1 as well. And this is always taken, so that's another 12. And then from B4 to B1, and then B1 to B2 is always taken again. So this is minus 48 from your true, and then you can add all of these up, and then you get minus 12, because minus 48 plus 12 plus 12 plus 12 minus 12. I can explain more if you guys are confused about this explanation. Yeah. Yes?
Explain that again.
Okay. So you're just basically counting the expected values. So you know that from the 120 iterations over here, branch 1 will always go to branch 2. So just remember that right side is always taken. From branch 2 to branch 3, you know that it's mod 2, so that's 50% chance that it's taken. So there's an expected value of 60 on the taken side and an expected value of 60 for the not taken side. For branch 3, which is mod 5, you know that there's a 1/5 chance that it will be taken. So 12 of those will go to the taken side, and there's a 80% chance that it will not be taken. So there will be minus 48 to the counter for the taken entry. So far so good? Okay. And then from B3 to B4, you know that since B4 is globally correlated with the second and third branch, then it's always taken on this side. And you don't have to consider the not taken side, because as soon as it's not taken, then it won't affect the taken table entry anymore. And from B4 to B1, again, we're assuming that B1 is always taken. So, well, branch 4 is always taken, I'm sorry. Here, and then branch 1 is also always taken. So after that, you don't have to consider anymore, because you're just looping back on the branch table history, or branch history table. Any other questions?
You guys want me to do the way the solution did?
Oh, no, I think he has a
The key is
question.
that the only way to access the taking, remember the global history register is through the B2, B3 path. It's the B1, B2 taking path. Like, there's no other way to access the taking register?
Yes.
Okay, all right. Yeah.
Cool.
Yeah, if you look at the solution, it's kind of similar in this regard. So in the solution, we factor out the, let me go to here. Can you kind of see it? I guess let's start from here. Right, so within each branch, let's start with B3. For B3, if you look at the code over here, it's the net value that would affect the entries would be first 1/2, right, for the that coming from B2, and then you multiply it by what is it? 1/5, which should be the taken part, which is also this one over here. This same branch from B2 to B3 and then taken to B4, right? And then the rest is not taken. So this would become plus 4/5, because you have a 80% probability of not taken. And then you multiply 1/2 over this 4/5 as well. So that means the contribution from B3, oops, okay. All right. So the contribution from B3 becomes 1/10 for the first, right? And then minus 4/10, which is 3/10. So that's for negative 3/10. That's from B3 alone. From the contribution from B4 is only taken. So it's just 1/10 in this case, because if you are over here, right, the probability for B4, which is in the code over here, to actually becomes taken is 1/10, and the not taken has already been factored out. So here's B2, B3, B4, negative 3/10 plus 1/10 plus. Now you want to do the same for B2, which would be in here 1/2. I mean, it's actually 1/10 as well. Right. So in the end, you get -1/10 for the entire thing. And then for B1, it's always taken, so it doesn't matter. Right. And then you multiply this by 120, so you get -12. Yeah.
Going back to the tree.
Yes.
Do we have to account for, so the final B2 is, it occurs in the global history registry, right?
Yes.
Or it occurs in the relevant global history registry, so we actually take 17 acres, right? So at that point, do we need to account for the fact that there's a 50% probability that B2 is not taken?
30%?
Well, that's my question. Do we need to account for that at all?
No. And where does the 30% come from?
There's 50%.
Oh, 50%.
50%.
No.
Yes and no, because there's a 50% chance it's taken and 50% chance it's not taken, so this can't take their own. Right?
Oh, I mean, valid, but then you can extend that recursively down the tree, right? Because then the next B2 has, right? Because the point is.
No, but each iteration is independent because it's just a random value in the array, so you can do.
Yeah, but the global history registry doesn't reset. So that might not matter after you enter B2.
No, it might not matter. But it doesn't matter because you only think about the taken path. So when you did the calculation, you only factor out only taken path already.
But B2, the point is that the B2 here is a taken path. Like the global history registry reads taken at the very bottom entry of B2.
And yeah, so it's from B4 and B1. Right? So B4 has to be taken.
Right.
And B1. So B4, but it's the last iteration, it doesn't matter.
But after it's taken again, then you're back up to the tree to the first B2.
Yeah.
And then if it's not
So if
taken,
you think about B4, you have to look at the perspective of B. If you're trying to figure out the B2 branch, you have to look at the perspective of B4. Because you have to make the GHR become 1 and 1, right? Taken and taken. And the only way you can have that happening is 110, because B4 is 110.
So the distinction is that, so we don't account for B2's values in the first iteration. Because
because
it's not taken path.
Yeah.
In the second iteration, we do have to account for B2's path, the path that B2 takes, but we don't because it's a 50-50 value. So
Okay. For the first iteration or second iteration, each iteration has no.
Well, because the global history register doesn't reset.
Yes.
So B1, in the first iteration, we start off with what, like 0, 0 or 1, 1?
B1.
It doesn't matter.
Yeah, it doesn't matter.
But in the second iteration, at B2, the global history register's value is indicated by B1 and B4, which means it's dependent upon the last iteration. It's dependent upon the path of B4 in the last iteration.
Yeah, it depends on B4. Yeah.
Yeah, which means that the second iteration actually is dependent upon the first iteration. So we can't immediately do that because the first B1 doesn't rely on. Right. The point.
No, what I'm saying is, like, if you look at the first or second iteration, it doesn't matter. The B2 will rely on the previous iteration of B4.
Right, precisely.
Yeah.
But this diagram doesn't account for that in the first B1. Right, the first B1 doesn't account for the fact that B4 might have different values.
Oh, but he didn't take into account of that upper branch. He account like everything from this point on to take into account all the branch.
Well, so my point is just
This
that
level.
if B2 has a non-50-50 value.
Yes.
The final iteration of B2 should actually should matter, right? So then this tree has to go one step further. Theoretically, if
Would
B2
go
is
to
non-50-50.
Right.
Because the should would cancel out.
Yeah, exactly. Yeah, okay. This is like a subtle point, and so it's not really that important. I was just clarifying.
Okay, cool.
All right. Yeah. Okay. This is like something something really small. I didn't want to like overbought.
Right. Any other questions? Right. Any more questions from the lab homework or? Which one is that? For which question?
This one, prediction and predication. I'm not sure I understand why exactly in the calculation you're including the number of stalls also in the calculation of branch penalty. In the calculation of branch penalty.
For which part?
For part A itself.
For part A.
Basically, now we're taking questions about homework and labs. So if you don't have any questions, you're free to go.
So, which machine you're talking about? The
I'm
branch
talking about
prediction or
this machine, the first machine itself. Okay.
machine A?
When the branch is taken and suppose when the branch is basically mispredicted. Okay, so in the execute 6 stage, I will be flushing the entire pipeline. But after that.
So once it's realized it's mispredicts, you have to flush out the entire. Yes.
Okay, after that, the next instruction would take me around. I mean, I'm not sure why you're including the number of stalls in the calculation of penalty cycles. That's all my question is.
Have you actually tried to draw out the execution of it?
Yeah, I saw this too. But once the thing is resolved in the E6 stage, the next instruction would take me around only as much as 17 cycles to execute, right?
Which? Oh, you mean the next? So is this a case where it's taken or not taken?
Just give this to him.
Okay.
This part of it where it says that